Well, welcome back, everyone. We're finally getting through this. We're now in week 3 of 16, but we're getting there. Any questions before we start out today's week? Okay, well, it's pretty much just a normal week as ordinary. We have our quiz number 2 that's due today, and our third quiz will be posted when we come back on Thursday. I don't have a ton of extra announcements, but I did want to also mention our first exam is coming up in 2 weeks. And so what you'll start to see on the Moodle website is probably as of this weekend, around Friday, possibly on Saturday, I'll be changing some information around here. We have the corrected due date that we discovered last Thursday, so that's why that's in red. But I'll be posting the exact sections I expect to be on exam number 1. With the pace we're going, I'm expecting we're going to be sections 3, 1, 2, 4, 5, and possibly 7 to finish it out. But once we get to the end of the week, I'll have the definite coverage that I'll list here, but I won't change it right after. I'm also going to post the little tidbits of information, such as it's an open calculator exam and the kinds of calculators are allowed, and that kind of information. I'll also be posting practice problems that are going to help out just preparing for the exam itself. So you'll see on a section by section basis, lots of typical problems that could end up on our first exam. So that's what we're going to be doing. Any questions, folks, at the moment? Yeah, go ahead. It's going to be from 2:30 to 3:45. So it's pretty much just like a normal class, other than everyone's just being really quiet and writing stuff down. So although it is a 75-minute exam, I'm glad you asked about that. I'm trying to write my exam so they're actually, in fact, 60 minutes. So it's expected you'll finish a little bit earlier, but keep in mind, please take that extra time to go over your work, make sure everything is about how you like it. If you're not sure what side of the fence you fall on, if you're not sure if a correction is needed or not, just go off your first instinct. That's usually the best way to go. But it's not a terribly 75-minute chock full exam. It's a little bit shorter than it seems. Other questions about the exam? Okay, kind of my goal with these exams, like I mentioned before, is this class is unusual. ISU math department does control certain aspects of it, like the homework, as well as they write the final exam. I will have sample final exams I'm posting down here, but I mention all that since kind of my goal is when I write an exam, I'm trying to prepare you for the final itself. I'm going to try to write the problems in the same kind of style, the same kind of formatting, so it looks similar. And when I write exam 1, that'd be my best attempt to kind of give you a feel for what the final exam will look like. So I write the exams 1 through 3, the math department will write the final exam. Other questions at all then, folks, before we get started? Okay, I guess we can jump right in. So we are now in section, 3.4, composition of functions. This one's not too bad to get through. I would say, however, 3.5, transformations of functions, it's a little bit more tricky than normal for our chapter 3. Anything that you can do before we jump into that notes at the start of that class is always going to be a big help. I always post these things. Read section 3.5. Part of it is to just give you a heads up that reading would help, certainly. Also, if there's just certain portions we're not covering, I'd always say you can skip this subsection or don't worry about this. So far, everything's been pretty much well included. But before we go to transformations of functions, if you do read that section 3.5 ahead of the class day, it will really help out. Even if all you did was open up the class text, go to 3.5 and you just skimmed the contents. Where is 3.5? Chapter 2, chapter 3, 3.5. If all you did was read just this, that skeleton of what's going to be in the section, that's actually enough to give your brain a head start. You'll know about what's going on, and it truly helps out. So even if it's a really fast, quick reading, this is all you read before you came to class, that's better than nothing. And if you have the extra time, try to go through more information. When you get to an example, say something like example 3, try to solve it on your own if you can, only looking at their solution once you're either done or if you get stuck, and it'll help you out reading as well when you're getting through these. Well, that's my announcements before we start off today. So let's go down to our section 3.4. That's a lot of back arrowing. Here, composition of functions. This is going to be a very, very algebraic-y kind of day. Less graphing, less graphs, and more just the nuts and bolts of dealing with recombining functions. Starts off with 4 different definitions altogether for the sum, difference, product, and quotient of functions. But let's get started by just first focusing on the initial definition. They say let f and g be any 2 functions. Now you could have wrote these as f of x and you could have wrote this as g of x. That's completely fine. It's a stylistic choice. But it's also fine to just call them f. That one whole symbol is going to refer to an entire function. Maybe it's linear, maybe it's, say, a square root function, so on. And then likewise, when you go to these things, f plus g is the name of exactly one function. It comes with 3 symbols, the f, the plus symbol, and the g, but that's just a brand new name for a new function, much like f was. And same for f minus g, f times g, f divided by g. Think of those as just a one overall symbol. If you go to any one of these, say maybe the product of the function f and g, what it's saying to do is take that new function, which we call fg. When we put x around it, now we're using evaluation, and this is the definition of what it means to take the product. All we do is we take the 2 functions, f of x, and I miscolored that, let me try again, and the other function, g of x, and just multiply their outputs together. But it's fg written this in like this in yellow that indicates that's what you're going to be doing. So the short of it, think of all these as the names of the functions, and everything right here, that's the actual formula of how you're going to be working with them. Does that make sense for folks at the moment? Awesome. Well, kind of our idea is just practice this table a few times. So example 1, example 2, it's going to go through these. And they gave us 3 functions, so let me call these f in blue, I'll do g in purple, and let's go, or g in green and h in purple. So first one it's asking us to do is g of g minus h of x. And pretty much this is how I would start this one off. G minus h of x. Again, inside that's one whole symbol, and the of x is just saying evaluate your brand new function. In fact, what some people might do, we won't do it in this class, but you might see some books that actually do it this way. The outer parentheses around g minus h is just a way to say that's one whole thing, one brand new thing, the difference of the 2 functions. So those parentheses are just to make it more readable, and this is the of x. But then when we go to use the definition, it says, if it's the difference, we'll just line up your functions in this kind of way. So I'll take g of x minus h of x. And that's how it starts off to that stage. All we have to do now is just drop in our function definitions and see what we get out. So this is what I mean by today's kind of algebraically. Once you go down here, we did one substitution already. I went to the definition and just threw in the functions that they gave us. It was g and then h. Now over here, we make another substitution. Look up the g of x function and write it in. It goes x minus 3 divided by 2 minus x. Then another substitution, we go to h of x, look it up. That one's a square root of x plus 3. So root x plus 3 would go here. And at this stage, we pretty much done it, folks. It's an ugly looking function, right? The first thing is what we'll call a rational function minus a square root function. But there's no like terms, there's no cancellations. We would just enter it into ALEKS exactly as it's shown. So we did it, folks. That's our first function so far. Any questions or comments at all getting through that one? Okay, in a certain sense, these definitions are nice. It's like the definitions that would make the most sense. If you're subtracting functions, do it in this way. If you're multiplying functions, just expand them out in that way and so on. But I think the trickiest thing about this is that request right there. Once we find the function, we also need to find the domain of that given function. So let's try it out right here for g of x, and then we'll go to the next one. I'll put a little border here just to indicate which portion we're focusing on. So now next we need a domain. I kind of like that they asked this question here, and ALEKS as well. It's a good review opportunity. The domain is all the possible inputs that you can actually use in this function. And we have a couple issues. There's issue right here. You can't divide by 0. So what would you say is the restricted value right there by the red dot? Yeah, go ahead. Oh, close. The whole denominator can't be 0, but that would mean x can't be 2. So yeah, absolutely. Does that make sense there? Gotcha. So like you're saying, we are avoiding a division by 0, so x cannot be 2 on that one. So we'll have to keep that in mind when we write out the domain. And then we do it again on the root function. Anyone recall what we have to do if we see a square root and we want domain? Exactly. Essentially, every time you see that root, as long as it's an even root, a square root like we see here, 4th, 6th, 8th root, and so on, you go greater than or equal to 0, take the input, x plus 3, and solve that inequality. Pretty quick, subtract 3 from both sides, and we have x has to be bigger or equal to a -3 altogether. So now we have to combine all this information. X is bigger than or equal to -3, and it can't be 2. So that means the domain looks like this. It's going to start right here at -3. But we can't go off to positive infinity because as we move across, we also have to avoid that 2 there. It's a little bit of an annoyance. So we'll go 2, throw in a parenthesis, union together with the set at 2. Now from here on, there's no other problems. We can go off to positive infinity. So that's what the domain would look like on this strange looking function g minus h of x. Well, it's kind of weird. The easy part is actually the new stuff. And I think the tricky part is definitely the domain. It'll be something we practice quite a lot as we go through this class. Any questions at all, folks, before we try another? Yeah, go ahead.
So with the first diagram of the domain, with the bracket and the -3, the bracket is the -3 because of the greater than or equal to -3, so it's included in that.
Yeah, exactly. Other questions so far? Okay, let's try this again. Next one is this function, f times g of x. But just for making this more readable, I'll put these little borders here so you know when the next segment starts. First thing I would do is you could write your function fg of x if you like. That little dot right there is just to emphasize we're multiplying the two functions together. Then after you write that out, we take a look at the definition up above on the table. It's unfortunately cut off, but let's not take a look at the definition. Let's just suppose we were to guess. If you're multiplying two functions like this, probably what you're going to be doing is taking your f of x. So I'll just write in this way, take your other function g of x. And essentially this is all you're doing. It's almost like the x distributes to fn to g as well in that kind of setting, same as over here. But that's only for the sake of an analogy. It's not a true mathematical distribution. It just happens to be the way this function is defined. Then take a look at the table. Let's see, it says if you take f times g of x, this is what your result should be. Just multiply those two functions together. So here we are. Now all we're going to do is make some substitutions and simplify. Does that make sense, folks, on this segment so far? Okay, so step one, all I did was I copied the definition of multiplying f with g. On step two, we're back to making loads of substitutions. So first go to f of x. Here's how it comes in. X minus 2 divided by x squared minus 9. Now over here, I didn't put in the multiplication symbol since it's not unclear what's happening. But if it's helpful for you, you can put it back here to say we're definitely multiplying these fractions. Go back to g and copy it in as x minus 3 over 2 minus x. And that's our function so far. Now we do have to simplify this thing, and there'll be a little bit of work to do with that. And when it comes to simplifying, usually factoring is a really good idea, especially if you're dealing with fractions. We would like to cancel things, and so we would like to have things factored nicely to make that happen. So here's what I would do on the next step. Here I'm going to drop the color coding since we're not doing as much substitution. On the first fraction, x minus 2, let's copy it in. But down below, x squared minus 9, we can factor this in a nice way. Anyone see how the x squared minus 9 ought to factor? Exactly, that good old difference of squares formula. We'll go x plus 3, x minus 3 on that one. Then we just do it again. Well, sort of. I mean, I wouldn't factor at x minus 3 up there. I'll just copy it in. But you know what? I would factor 2 minus x. Anyone see a way to factor that thing? It's a weird factoring, and the reason I'm factoring it is 2 minus x feels awful a lot like x minus 2. Would you all agree? It's really just off by a negative sign, and you can factor out just a full-on negative sign from that. Here's what it might look like. Factor out a negative, I'm going to put in parentheses. Now you could put in negative 2 plus x if you prefer, but it looks just as well as x minus 2. Double checking, if you wrote it that way, distribute the negative sign in, that gives us the negative x, which we want, and now we have. Distribute it to here, it's negative 1 times negative 2, which gives us a positive 2. So that's our factorization there. It really does work out. Now, here's the big punchline. The reason we did a weird, kind of a tricky factoring on 2 minus x to get that is because we can now cancel from the numerator to that denominator, just leaving the negative sign. Likewise, this x minus 3 can cancel from numerator down to denominator to get that x minus 3. And the whole thing just turns into, let's see, don't forget the negative sign. That'd be the easiest way to miss a point on Alex. There's going to be a negative 1 over x plus 3. So that's how the function goes in its most simplified form. Now, this one is extremely tricky when it comes to domain. So we'll cross that bridge in just a moment. But any questions at all with the substitutions or simplifications? Okay, so here is the weird thing about domain on this. When you go to find domain, we need to focus on this portion before cancellation. I think that's important enough to make a note on this one because it is so easy to miss a point on a domain thing and just never understand what went wrong, what we missed on it. So find domain using the functions before cancellation. So that's the major thing to watch out for on this one. Let me drop this to another page. Oh, and try a little bit harder. There we go. So when we go without before cancellation, rather, sorry, struggling with Microsoft Word. Let me just hide example 2. There we go. That means we're back to this denominator. We know what factors as x plus 3, x minus 3. And so that means from the blue, x cannot equal positive 3 or a negative 3. Let me fix my comma though, that looks weird. You could see that from either here or right here as well. Put in a negative 3 in that location, you divide by 0. Put in this location and you've also divide by 0. Then back to green, 2 minus x. Anyone see what x cannot be from that location? Exactly, we cannot have a positive 2 there either. But let me mention, this is what makes it so tricky. We worked really hard on simplifying this function, right? I paused right here and said there's 3 domain problems, positive 3, negative 3, and positive 2. But then we simplified all the way to here, and that one only has 1 problem at negative 3. So the question becomes, what is going on with math? Where's the lie? And it turns out to be right here. This is one of those things where, even though we say equality, it comes with provisions. That equality is only true if x is not equal to 3, negative 3, and 2. In other words, all of the original excluded values before any cancellation still affect the domain right here, making this one extra tricky. This kind of thing happens whenever you're doing a cancellation, especially if it's with fractional type of functions like this. Well, any other questions or comments about this so far? I mentioned we're not doing a lot of graphs today, but how about just one graph on this one, just to see what's happening with his domain entries? Is that all right to folks? Okay, so pause your thought right here. Let's put these actual functions right into Desmos. First function is f of x, which is in blue. So I'll just write in f of x equals x minus 2 divide by x squared minus 9. So there's our first function, and it has two problems, one at -3, one at +3. It's kind of neat. You can just sort of see those are what the problem values are on that function. Next, g of x is the function right here, x minus 3 division by 2 minus x. So that's the function in blue. But what we're really after is f times g. So we'll say here, fg of x is equal to f of x times g of x. If it'll allow us to do that, maybe not. Oh. F of x, there he goes, times g of x is this brand new function. Let me turn this off so we can study it. There's our function. Now notice there's a problem right at -3. That's where we said there's a problem here, but I also said +3 and 2 are still a problem, even though you might not be able to see it on the graph. But let's take a look even closer. When they sketch this graph, they're connecting the dots. And one thing they're leaving off is where all the holes are on this graph. -3 is one of them. Let's take a look at +3. It's right around here. And right at +3, if I can settle there, there is in fact an open circle, and they say it is, sorry, this is really hard, undefined right at that location. So even if your graph looks nice, there is still a hole on it if all you did was this, multiply those two functions. To me, that is really bizarre and something to absolutely watch out for. Another one, let's take a look at +2. At +2, if we go really, really close right here. Oh, there we go. Notice the circle turns into an open circle, but it's kind of hard to see. And it says undefined as well. So that's the next problem point. All this is just a big reminder because, again, this is a technical issue that causes havoc on a homework set. If you have a fraction and you simplified, check the domain before cancellation, because that's how we really produce it. Does that make sense to everyone at the moment? Okay, last thing to do is write down this domain. Unfortunate side effect is if there are three problem points, then our domain comes in 4 segments. So it would look like this. Domain. First, we can start off at, say, -infinity until we get to that -3 there. So with parentheses, -infinity to -3, union, then we start going off to the -3 to the right. The numbers get larger and larger, across 0, 1, until we hit 2. 2 is a big problem point, so we'll put it around a parenthesis, and then all the way up to +3. So far I'm saying all negative numbers up to -3, excluding it. Then all numbers between 2 and 3, excluding the boundary points. And last bit, all numbers larger than 3 will also work. So 3 off to infinity. Finally, that's the full domain on this tricky function. Yeah, go ahead. Oh dear, yeah, I kind of just skipped it off. I did say there's 4 segments, but then I think my brain just kind of did a micro sleep right there. Thanks for spotting that. Let me try one more time. I'm going to go from -3 to 2 on this one. Then go from 2 to 3. I think that's where I skipped to right on that one. And then finally from 3 off to infinity. Let me put a little border around this. Thanks for spotting that. Does that look better to everyone? Awesome. And notice again, that's a terrible thing to have happen to us. If this was an Alex problem and I just forgot that one piece, well, I've had a lot of extra practice. So go a little bit slower, double check your results, and you can save minutes of time on Alex, which is always a good thing. Well, one last one. Any questions so far, folks, or comments? Okay, I'm just going to scroll for a moment to remind myself what were the functions and what we're about to do. Occasionally I'll take little screenshots like this so I can just walk it down and not scroll up and down constantly. So our last one is h divided by f of x. So right here. First thing, always good to just write down what you're about to do. It'll help if you look at your paper again. So h over f at x. Next thing, we're going to look up what the definition is. But if there's a function division, it really should just be h of x to start, divide by f of x, and I think we did that one in blue. Let me fix my colors here. And so that's how this should go. Now, when we take a look at this definition here, we used this portion, and it had just a little bit of extra instructions. This definition works only if g of x does not come out as a zero. So we'll have to keep that in mind, especially when we take a look at domains. But from here on out, it's really not too bad. We do as we did before, look up the functions and substitute them in. So let me write equals. First will be h of x, just an ordinary root function. So root x plus 3. Divide the whole thing by f of x. And well, it's going to turn into a weird fraction, but that can happen. The denominator of my fraction is an entire fraction of x minus 2 divided by x squared minus 9. So we can delete that. That was just for a quick reminder. And go from here. Any questions at the moment, folks, before we simplify this one down? Okay, if I were to simplify this, honestly, there's really not much to do here. There's not going to be any cancellation. And all you're doing to simplify is removing the fact that that's a complex fraction. It's a fraction with a fraction in the denominator. The go-to method would just take this whole thing, keep the numerator in place, root x plus 3, and multiply by the reciprocal of the denominator, which is a fancy way to just say flip it. So x squared minus 9 is now a numerator. And x minus 2 is the denominator. If you write out like this is algebraically correct. You're saying root x plus 3 is multiplying this whole fraction. Another algebraically correct form could look like this. You could just take root x plus 3 and multiply it into the numerator. There's lots of valid choices. What I probably wouldn't do is distribute the root x plus 3. That would make it more complicated than it has to be. But now at this stage, we're ready to find the domain. Any questions at the moment first? Okay, now this one gets tricky, not because of the same issues of what's going over here, although it's similar. It's going to get tricky because of this portion. We just used that definition. Let me just drop it down here for easy reference. And when you go to find the domain using that definition, you have to pay special attention to the denominator right here. So keep in mind, f and g is flipped. I have h and f. So I go to the denominator, take a look at the f of x, and consider this condition. F of x cannot be 0 at all, or else we're not having a domain entry. So let's take a look at f of x and solve for that. I'll put here domain just to indicate now we're solving for it. F of x equals 0 implies, well, what was f of x? It's x minus 2 divided by x squared minus 9 equals 0. So that's what the equation would look like. All I did is substitute in the value for f of x on the left, and the equal 0 came from this condition. First, I'm solving how to get it equal to 0, and then I'll say x cannot take on those values. Anyone happen to see what the one-step solution would be to that equation? There's a trick involving in this, which is kind of fun. Yeah, go ahead. Unfortunately, we can't square root just the 9 independently. We would have to root the whole function if we want to involve a root. But there's still a certain way we can go at it. Any volunteers? Yeah. Exactly. What's really silly about these kind of functions is, or equations, excuse me, they look complicated, right? But you can always just say, take that whole denominator, do a halfway cross product, you're feeding it to 0. It's all about the numerator, really. I'm going to show the full steps right here, but this is a shortcut that's highly encouraged. X is 2 immediately when you see this equation, because if you plug 2 into that numerator, you would get the 0, and it balances at 0 equals 0. Just make sure you don't get 0 below as well. But if we took the long step, here's what it looks like. It's really not too long. Take x squared minus 9. Multiply into both sides of the equation, and here's what happens. Cancellation there. There's in fact a cancellation on the right because 0 kills off everybody. It doesn't care what the function is. And you get to this equation. X minus 2 equals 0. Add 2 to both sides, and x would be equal to 2. But remember, we are solving this information, so we want to really say x cannot be 2. Or else, well, we divide by 0 right exactly here. It'd be 0 divided by 4 minus 9. Does that make sense to folks on that first issue here? Okay, well, it gets more exciting because when we look at this function f of x, I can't plug anything into the denominator that would result in a 0 either. So I can't put 3 here. I would get 3 minus 2, which is okay. But there, that would be a 0 inside of a fraction. So all those domain issues that we're getting, even right here, x cannot be 3 or negative 3, it still applies to that function f. So let's also say here, f of x equals x minus 2 over x squared minus 9 means x cannot be equal to negative 3 or positive 3. Let's just collect those issues over here on the left. Negative 3 and positive 3 are all big issues. So let me put here, we went 1. My first step on finding domain was I was looking at this information for when the denominator function goes to 0. On step 2, I went to here and wondered, well, the function f of x itself, is there any way to get a domain entry? Absolutely. You can't have 3 or negative 3 due to that denominator. And here's step 3. There are more issues on this one. Anyone see what they might be? Well, sorry, go ahead. No worries. Well, remember we have a square root function, right? So I still can't put in like negative 10, can I? I can't even put, say, negative 3.1 or anything. So I still have to use the fact that x plus 3 has to be bigger than or equal to 0. There's just no getting out of that, which would mean x has to be bigger than or equal to negative 3. I'll collect that over here on the left. X has to be bigger than or equal to negative 3. Almost there, folks. So now with all of this thrown together, we need to write the domain in interval notation. So here is my final step 4. So in orange, these were the steps I took to find domain, but this is the ordinary stuff right here, just cranking up the function h divided by f. But finally, the domain and interval notation would look like this. I want to find the smallest value I could ever put in. Anyone see what it would be? Yeah, go ahead. Exactly. I'm glad you said that. It's tempting to use a bracket, right? But from right here, we can't include it either. We'd divide by 0 if we did. So it's really going to start like this. A parenthesis, I almost made a bracket. It's so tempting. Parenthesis, negative 3. Then we just go off to the next largest element in the domain. So negative 3, after that, I'll have a problem at a positive 2. So from negative 3 to positive 2 with parentheses, then union, we're going to go from, let's see here, positive 2 all the way to positive 3. So 2 comma 3. Then anything larger than 3 is just fine. You had to be larger than negative 3 on that one, the square root. So I'll go parenthesis 3 comma infinity. Finally, that does the job for us, folks. That's the domain of this function. Any questions at all on getting through these? Yeah, go ahead.
For the negative 32, when you put like that, and the negative 32.
Only reason we did put negative infinity here is because it had to be as the minimum a -3, not including. Negative infinity would have said you're also including like say -10, -50, and so on, larger and larger negatives. But because of what's in, I guess that's purple right here, we only started at -3 on this one. Definitely a little bit weird. If there was no square root here, we would have expected a negative infinity on the far left, like you're saying. Other questions about these so far? Okay, so domain, definitely the trickiest thing about this. I'd say definitely take a little bit extra time and look at the weird issues that occurred on these notes for inspiration. Watch out if you get fractions, especially watch out if those fractions cancel because you find your domain pre-cancellation, not out here post-cancellation. Well, those are the main takeaways on these topics so far. But what was happening on these problems was, notice our answers were actual functions like we see in black. Some of them are complicated, some of them simplified. Other times when you do this, your answer is going to be just a number. And that's the purpose of example 2, a little bit more streamlined, I'd say. Here, we have 2 brand new functions. We're calling them R and S. I'm only doing this because you'll see it in the homework. S is a terrible way to label a function because you want to avoid making it look like the number 5. So that's going to be our major goal on these notes. It says just evaluate these 2 things, R times S at 2, R plus S at 0. Again, there's numbers here, not variables. And so we're not expecting a function. We're expecting a numerical result when we do these computations. Color coding could help, so let me just copy that strategy again. I'll do R in blue, S in green. I guess we could just start off with this one, R times S at 2. And I'm going to try really hard not to make that look like number 5. First thing we want to do is just use the function definition. And the definition says, take your function R, but this will be R at 2, not R of X. Multiply it against S and S at 2 as well. My 2 got damaged, so we can see if I can fix that. There we go. So that's how the work starts. Next, at this stage, we're just making some substitutions. This 2 in blue is going to occur or change that X value right there. And so all we're going to get is, let me copy in the function 8 minus 3, where X occurs, we'll just put in the value of 2 and square it. So that's the entire punchline to what happens to R of 2. Now go to S of 2. Inside here, it starts off with the X, so we'll put the value of 2 right there. And just call it 2 plus 3. From here on out, you could just shove the whole thing to your calculator or do a couple fast by hand computations and see what we get. Usually I do these by hand because it's honestly good practice. In this first parenthesis, it's going to be 8 minus, order of operations says square the 2, we have a 4, multiply by -3, so we'll get a -12. This one, parentheses weren't as needed. You could just drop them and say it's 2 plus 3 to get a 5. So now we have -4 multiplying by 5, or a nice round value of -20. So that's our first evaluation, and the question didn't ask us about domain, so that's almost a cause for celebration. Not every problem analysis is going to be terrible. Some of them are pretty dang quick like this. Any questions at all, folks, on finishing this one? Okay, that went really fun. So let's try this again. R plus S at 0. So copying it in, I have R plus S, evaluate at 0. And this is a good reminder about function notation. If you didn't take any class involved function notation, but you knew a good amount of algebra, you might have said, this is silly. Why are we doing this? It has to equal 0, right? Well, no, it doesn't, because that's not multiplication. It's function evaluation. we're sending the number 0 into a brand new function called r plus s, and I have no idea what that function is going to do. First thing we do is go to the function definition, where we'll take a r of x function. Oh, I already made a mistake. Let me try this. It's tempting to put an r of x, but if you have a number 0, that's the better thing to do for sure. I'm taking the r of 0 plus. Now go to the s function. This will be s of 0. Now all we're doing is evaluating both of those functions, adding those results together. So for blue, r at 0, it'll be 8 minus 3 times 0 squared. If you just call that 8, you saved a lot of steps, but I'll usually just write this kind of stuff on the notes so you know what happened when you come back to read it. Then plus s at 0, we go to the s function, throw in a 0, it's just a 0 plus 3. Again, those parentheses aren't required, it's just my habit, being really, really careful on these evaluations. If you're not using them every time, no harm done, but sometimes they are required, so it's a decent habit. Well, we're just about done, right? This is just going to turn into 8 minus 3 times 0, so just a 8, plus 0 plus 3 is just 3, so we're up to 11. And that's how this function ends. It's a weird kind of problem because the way I did this, it's really just pure arithmetic with some substitutions thrown in. There's no reason to do r times s at x and then plug in 2 in that result. That would take about twice as long, maybe even longer. And what's so bad about that? If I take twice as many steps, my chances of making a simple mistake go way, way up. So it's always good to try to find an efficient way to get through these kinds of things. Well, we did it, folks. That's example 2. Any questions at all on getting through this one? Awesome. Well, I do have a word problem today. None of the word problems we're doing are really all that serious. Usually they're just an extra topic that goes along with the current section. But I felt like this is a good extra topic for us to do today, since some of the word problems are not as easy as others, I think. And this is one of them. I brought 2 of them to the class today on this set of notes. So to start off, here's how it goes, our scenario here. A small publishing company is releasing a new book. So that's exciting. It says next, the production cost will include a one-time fixed cost for editing and an additional cost for each book printed. The total production cost, C in dollars, is given by this cost function, 550 plus 15.95 n, where n is the number of books. It's a lot to process, so let me first think in these terms. Production cost, well, they gave it to us as a function, so I'll think of that as a function in blue. N is going to be the number of books. I'm just going to highlight that. They didn't give us that as a variable. They just said that's what n represents. Sorry, I said that in a funny way. They gave it to us as a variable, n, number of books, but they didn't say it as a function. So I'll just highlight that in gray. Now next they say the total revenue earned in dollars from selling books is given by this function. So this is in dollars, $32.80 times n, the number of books. That'll be how much revenue you're generating. And next they say, let P be the profit made in dollars. Write an equation relating P to N and simplify. So when I read that word problem, it doesn't sound fun. It sounds like a lot of stuff to untangle, but you'll see one just like this, and it's really not too bad. Here's how it gets started. There's a cost function, and then there's also a revenue function that they gave us. Let's maybe think of this one in green. We have a next function, a profit function. I'll think of this one as being in purple. And it says relate P to N. First thing we need is a formula. And here's how I'd get started with this one. P for profit is going to be equal to, first, the amount of cash you started accumulating after selling the books. That's the revenue, the cold hard cash. But this is not how you pay your bills. You still have to pay for the production cost. So you take all the revenue from selling the books, subtract away the cost for making those books. We've got to pay our bills somehow. And this is the function that they're asking us to write down. So really, it's just a really fast way, this one word problem, to do this, the difference of two functions. But some of these take a bit to break down. Anyways, you can find different ways of seeing what are the two functions you're combining together to get a third function can help out quite a lot, whether you're color coding or doing something different. But at this stage, all we really have to do is write it down. It says relate P to N, but this is how it happens. P for profit is going to first be, let me get the revenue function, and revenue is 32.80 multiplying N. And now I'm pretty much just copying and doing more substitutions. Copy the minus, go grab your function C, and it substitutes in as 550 plus 15.95N. Now, I'm going to make a mistake. Let me know if you can spot it and how to correct it. 550 plus 15.95N. Anyone see where the mistake is? Yeah, go ahead. Exactly. Whenever you make a substitution right here, parentheses are a great idea. And it's not just a great idea if you have more than one term, it's absolutely necessary, like you said. Everything has to be multiplied by that negative sign right here. And so I absolutely have to have parentheses right here for my next steps. Super easy to miss, even if we have the right function and the right breakdown. Well, any questions, folks, with our work to this step? Okay, when they say simplify as much as possible, well, they're just seeing what we did with that negative sign, really. They want to know if we distribute it correctly and got a right answer out. So let's just start writing this in as P equals 32.80 times N. Distributing the negative sign in will give us minus 550 minus 15.95N. We do have to combine our like terms, so we'll take 32.80 minus 15.95 copies of N. Here's my really fast calculator. So 32.80 minus 15.95 gives us a value of 16.85. So 16.85N minus 550. So this is how much cash you'll have at the end of the day after paying all the bills for actually creating all those books. $16.85 per book, and take away $550 for the startup costs of making them all at once. So that's really all they're expecting on these kinds of problems. The word problems are going to be kind of light like this until we get further on into actual full-on application sections. And you'll know when that's coming in. I'll make sure we spend extra time on those. Well, any questions at all, folks, on running through this one? Okay. Well, we pretty much did the first half of the notes. We're doing the arithmetic of functions, adding, subtracting, multiplying, and dividing functions. And this example 3 is just showcasing worthy application for all that kind of work. Next thing we're going to take a look at is function composition. It's tricky in its own way, but when you get fluent with it, it's not so bad. Here's the main thing that's tricky about it. When we do function composition, keep in mind, it's not this. That's an entirely separate idea, and it's easy to get them mixed up. In fact, let's put a warning here just to be extra cautious. This is not function composition. Function composition is, well, I mean, it's a weird name, first of all, when you say composition. When you say stuff like composition, you're saying, how are things composed? In this context, a function composition means one whole function like f is going inside a whole other function like g. The resulting functions compose in parts by putting one inside the other, essentially. And the way that looks as a formula is this. So this right here is function composition. It's written in a strange way to start. It says, for any input x, the functions f and g, we have the composition of functions, which we write this way. Now, that's a weird symbol, and if you haven't seen it before and you read it as fog, that's completely understandable. I mean, that's what it looks like to me. But if you really write it just with a normal penmanship, the O looks like a degree symbol, but it's midline. It's not the bottom, it's not the top. And this is read as F of G. So that little O there, think of it as of, and we're just essentially saying, if we look at this definition, the function G is going inside the function F. That's what we mean by the composition there. So if we color code these, F can be the blue function, G will be the green function. F of G, that's just the name of the function. It doesn't even tell us how to calculate it. That's just how we talk about it. But this is the way we actually compose. G of X, that's not going to be helpful. Let me fix that right away. That should be a green, goes on the inside. And it's going inside the F function in that way. So we'll keep an eye on this and give it a try right away. So I have two functions, an F of X, on the F of X here being blue. And a function G of X, let's go green as well. And we're doing two function compositions, F of G, and then we'll do G of F. Reason we're doing twice is they're not necessarily going to be the same, which is really weird. And it's extra weird because if you multiply functions, F times G, that's the same as G times F. Multiplication is commutative. 5 times 3 is the same as 3 times 5, in other words. But function composition is absolutely not commutative. And we'll find out why when we give this a try. So I'll start off with F of G of X. This really doesn't do anything. It's just saying that's the problem I'm about to start. That's good to write that down, even though there's not much there. It reminds you what you just calculated. This is maybe the bigger thing. F of G of X is defined in this way. We take the F function. Sometimes we call it the outer function. Then take the G function. This one's the inner function since it's going inside F. And that's the big formula really right there. If you've got this red part down, then every time you see F of G, just follow that pattern. But keep in mind, it matters what comes first. It had to be F. And it matters what comes second. It has to be G for your work to look like this. Does that make sense to folks to that stage? Okay, now, well, today is a heavy algebra day, which means we're doing substitution after substitution after substitution. And here's how it's going to go. First, just write down F. We're not going to substitute anything there for the moment. Put in some parentheses just like before. And my first substitution is just to say, what is G of X? We go look it up. It's 2x minus 3. And we plug it in where G of X was. So that's our very first substitution. Does that make sense to folks so far? Awesome. If you think back to Alex section, I believe it was 3.2, you've actually done computations like these. H of X divided by 2 or H of 2X, G of X plus 3. Those were all function compositions like we're doing right here and now. And the next step in those compositions is to do the following. When I go to make my next substitution, I'm first looking at the function F. Here we're going to go really, really methodical. Every time you see an X, I highly, highly encourage you, put a placeholder, just an ordinary set of parentheses. So in place of X squared, here's my parentheses squared. No more X's there, so just minus 3. And then the input, 2x minus 3, goes anywhere X was. So it's going to go into this location to start. Then there wasn't any further X's, so we just stop here. Now we have to crank this out and see what it simplifies to. But if you can do those two kinds of simplifications, then you're doing great with the function composition. Does it make sense, folks, on what went where? Okay, if you like arrows, here's the kind of thought. The G function went inside the F function in that kind of way, and that's essentially all that's really going on. Next, I'll go back to black. We're done with our substitutions. If you get really good at squaring these, you could just write down the answer, but occasionally I'll put this in. 2x minus 3, 2x minus 3, minus 3, just as a reminder, these have to be FOILed out. So distribute 2x in first, we'll get 4x squared minus 6x. Distribute the negative 3 in second, there'll be minus 6x plus 9. And that's not a bad set of steps to take. If you wanted a shortcut, it really goes like this. 2x squared is the 4x squared. We'll get negative 6x twice, so really negative 12x, and then plus 9. So if you write down your work like that, I'll just assume you've done these lots and lots of times, and that's always okay. Last thing I have to copy down is the minus 3, and just combine our like terms. So there's a 4x squared. There's negative 12x's, and 9 reduced by 3 will be the plus 6. That means we did it, folks. That's our function composition. If there's no like terms to combine, there's nothing to cancel, you're in great shape. You don't have to factor these unless they ask you to. That would just be extra steps with no apparent benefit. Well, let's try this again. First, any questions at all, folks, on that composition? Okay, next, we'll do g of f at x. So it goes like this to start. G of f at x. Then we have to be very careful of what came first. This time it's the g function. The f function is coming second, and so the formula would really look like this. Take g of f of x. Lots of ofs when it comes to compositions. Now we just take a look at what were the functions. Let me hide example 5 and see what it comes out as. Let's make our first substitution. All I'm going to do is say, what is the function f? So I copy g. Now for f of x, go way up here, and it's x squared minus 3. So that's substitution 1. For the second substitution, it really does look odd because all I'm doing is I'm looking where g is, go up here, putting huge parentheses wherever x emerges. So it looks like this, 2 something minus 3. That's the substitution of the g function. And this x squared minus 3 just gets inputted in this way, x squared minus 3. Notice this composition is the easier one to get through. All I have to do is distribute 2 in, combine like terms. We didn't have to FOIL like we did on this one above. So this turns into 2x squared minus 6 minus 3. So it's all together 2x squared minus 9. Well, we did it, folks. That's composition going one way. F of g of x gave us a trinomial, 3 different terms. G of f of x gave us a binomial, 2 different terms. I mean, they're both quadratic, but these are not the same function. So the related takeaway here is that f of g at x is not the same as g of f of x. Well, any questions at all, folks, getting through this one? Okay, that's what function composition looks like if we're dealing with just ordinary functions like these 2 right here. If we're doing it numerically, only difference is they might ask you to do f of g at 10 or maybe g of f at negative 3, something along those lines. Well, let's try that out next just to see how that goes. And then I think I do have one word problem that goes along with composition as well that we'll give it a try. So next, for example 5, I have 2 odd-looking functions, a p of x function. This is almost how you can really guarantee this is motivated by Alex. Sometimes they like p, q, s, and t for functions. Here's the next function, q of x. So p is just a linear function, but q is a square root function. Good thing we're not doing the domain on this. They just ask us, evaluate q at p at negative 3. So let's make that happen. Q at p at negative 3. Just like before, we have to pay special attention to what's what, which function goes with which. So the outermost one, q of x, goes here. The inner function will be p of x. And here's how we work it out this time. It always feels different versus if you have an x, like the prior problem, versus a number. The number ones are a little bit easier because we can go like this, go q at. Now, when it says p of -3, I'm going to make that substitution right away. -3 is going inside that location where x occurs. So I'm copying in the p function with a placeholder for x. It looks like this, 10 times a parenthesis plus 50. But the thing going in that parenthesis is that input of -3 right here. Just to help track what went where, let me put that one in yellow as well. But once we get to this stage, before we worry about Q, let's think in terms of order of operations, filling out what all this turns into as a single number. This will become equal to Q at. Inside the parenthesis, this is -30 plus 50, so we're going to get 20 altogether. And that's our next operation to work on. So, well, Q at 20, that's not too bad. We just take the Q function, this one here, and input 20. Does it make sense to folks on how the steps work out for this kind of situation? Okay, so let me go and write equals, converting this to green, and I'm just going to copy in the Q function, the last one. It goes root of twice something plus 9. And we found that that something is this 20 right here. We'll input into this location and turn our square root crank to see what we get. This becomes the root of, that'll be 40 plus 9, so we're up to 49. And that means we just get 7 altogether. So we did it, folks. That's the work we'll have to get into for this kind of scenario. If it's just numerical values, you should get a number as a result, like on the first set of problems. And just by the way, which one looks less tricky to folks? Do you feel like it makes more sense with variables or with numbers? Any preferences? A little bit more with numbers. I tend to agree because this whole thing, if it was a variable, I cannot simplify it. I have to work with it exactly in that format. But if it's numeric, you save huge amount of times just calculating it and getting your value right there. In other words, I can't compress x squared minus 3 into just a number. That's as simple as it gets. Well, any last questions, folks, before we try this out with another? Okay, I believe I have one more problem similar to these, just on dealing with composition. And then at the very bottom, I have a word problem as well. This one's not too bad, but it is one I want to solve. So if I can't get this one done today, we'll start off next class with it. Let's just see where we end up. Reason I don't want to rush through to try to get to that word problem is I just spotted it asked us to do something about domain. Always have to be a little bit careful when it comes to domain. So we'll take our time with this one and see where we end up time-wise. We have two functions, a g function and an h function. So I'll color code them like before. It says, find the composition g of h. That'll be the easy step. Then specifies domain. That's probably easy too, but it comes with trickiness, so we'll be very careful there. First, we start off, let's just copy g of h. Even though that's 3 symbols, that's all one function. And so if we're going to calculate it, we put parentheses around it to just help our eyes see it's one thing. And we're inputting the variable x. When it says find the composition, that means this one is not numeric. We're throwing in just a generic x to see what form it takes on. So let's be careful with this one. We'll start by writing that this is the g function of the h function evaluated at x. So that's our next stage. Now we get to substitutions. First, just write in g. In place of that h of x, Move over to here with your finger or your eyeball, and it's a 4x minus 11. So it goes into this location, 4x minus 11. That finishes off one substitution, and so that was so fun. We'll do it again for g. This equals. Now where you see this g right here, oh dear, it's a fraction, so we're going to be excruciatingly careful. X occurred twice on this one. So that means in the numerator, I'm going to put in a big parenthesis, plus 2. And for this denominator, I need to do the same thing, and then plus 3. So big parenthesis, plus 3. To me, this is where the function composition gets pretty tricky. If x occurs in more than one place, the input to the g function, 4x minus 11, goes in 2 locations as well. If x appeared in 3 locations, expect 3 spots you have to throw in your g function. So we'll go here, 4x minus 11, and here, 4x minus 11. Any questions so far, folks, to that stage? Yeah. Right here. Oh, yeah, that's a comma. Yeah, sorry for that weird distraction there. Sometimes they help, but honestly, sometimes they're just distracting, especially if I'm zoomed out too much. Other questions or comments so far? Okay, well, we did it, folks. All we have to do is simplify that thing, and it's really not too bad. The parentheses here are that's a hard word, are unneeded, and so we'll just drop the parentheses and add up the numbers. It's going to be 4x minus 9. Down below, 4x minus 11 plus 3 would be 4x minus 8. So that's our brand new function. Now all we need to do is find the domain of this function and see where we end up. Any questions at all so far, folks? Okay, first thing we have to take a look at is what was the domain of the inner function, the h of x? So let's start with domain of h of x is, and honestly, to me, this is a tricky question. I'm not looking at the whole answer, the g of h of x, just this one piece. So if that's our function, 4x minus 11, any volunteers for what the domain should be on that one? Good call, all real numbers. To me, what's tricky is when you're trying to calculate a domain, you're looking for a problem, right? Or how do I divide by 0? How can I make my square root negative? Those are our big things. But this one has no problem. It's just an ordinary linear function. And that always has all real numbers for domain. So I'll write it this way, negative infinity to positive infinity. Now we go to this one. Well, here you cannot let your x become a negative 3. But this g of x is less of a problem. The reason is, when you throw this x inside, we first have to make sure that x is inside the domain of h. For in business, the domain is all real numbers, so no problem. We also have to make sure that x doesn't result in a value, so that we divide by 0 in this result down here. So we go to this function, the 4x minus 8. And from here, we have another domain issue. We can't allow that piece to go to 0. So we need to look and see what ways could you pick an x to make that 0. Exactly, some people are indicating 2 is the problem here. You could go 4x minus 8 equals 0. So 4x equals 8 and x equals 2. But remember, this is just solving for the problem point. What we really want to say is x cannot be 2. So finally, we can put all that together and assert that the domain is equal to not quite all real numbers. That's just what you can put into h, but you cannot pick an x as 2. The moment you do that, well, there's no problem down here, but the problem emerges right in this location. We'll have a division by 0. So we'll say here from negative infinity to 2, and then union from 2 to infinity. What are your questions, folks, with the solution to this one here? Okay, well, that's domains and ranges. That's the tricky aspect of this. Think of that as more review. If these were real exam questions, I'm not going to ask the hard domain and range questions here. Yeah, go ahead.
So the whole goal for us to get that last one that you just showed us was to have the number, or was to have the X value be something that made the denominator 0, is that correct?
Yeah, exactly. So X couldn't be 2 right here, because if you plug that in, we've divided by 0 essentially. Other questions at the moment? Okay, well, we did come back from a holiday, so let's do something slightly different today. I do have one additional question, example 7, but I'll leave it up to you. Should we give it a try or should we save it for Thursday? Your choice today. Go for it. All right, we'll give it a try. Thanks for taking the lead on that. So example 7 says, we have an area function. It says the area, A of R in square meters, of a circular algae colony with radius R meters is given by that function. So we have an area function thrown at us. They next tell us that the radius, now this is a weird way to indicate radius, M of t. I probably would have used R for radius, R of t, but it's their function. They get to pick the words. The radius M of t in meters after 2 minutes is given by this function. So there's the radius function. And it says next, write down a formula for a third function, z of t. Z of t is going to be the area in square meters for the algae colony after t minutes. It almost feels circular, right? Because they just said A of R is the area in square meters, much like z of t, but that was for the algae colony, which depends on radius, not time. We want a function that depends on time, not R. So we have to put one function inside of another, and this is how it's going to go. I would write z of t is going to be equal to, there'll be a function composition, but my question for the class is, which function is going in which? Is the radius M of t going inside of area, or is the area A of R going inside of radius? Definitely kind of tricky, right? But one thing you can say here is, when they said the radius is M of t, we have a radius right there standing for R. Essentially, this goes there, if you like arrows. That's the way the composition should go. The radius function, which they called M, is going inside the area function, which we call A. So if I was to write this out as just a step to indicate what I'm about to do, I'd write it this way. Area function is taking an input of a radius function M at t. So this is, again, kind of a strange word problem. We're throwing one function inside of another, but at least it's nice to see a context that would go along with the function composition. Think of that as the main takeaway of this problem, even though once you get to this step, it is pretty fast. Here's what the rest of this is going to look like. We'll have area of M of t, we just look it up and substitute in its function value. It's 14/3 of t. Once we have that, we're going to take 14/3 of t, plug it inside the area function like it's indicated, and the next step would look like this. The area function goes pi, then it takes a radius and it squares it. So there's our function. The radius going inside is this thing, 14/3 t. Well, if this was a real ALEKS problem, I think they're probably going to want us to square that out. If this was, say, a problem on a homework or a quiz, I'm pretty happy with the way it looks right here. There's no real simplification. If you square 14, you get 196, which you have to then multiply pi with. Square 3, you get a 9 down below. And you still have to square t, so you get a t squared. This is about how ALEKS is likely expecting it. They're probably expecting our t squared to be in the numerator as well. We did it, folks. That's the function that's going to give us area with respect to time, we have a variable t. We don't have a variable r instead. Well, any questions at all, folks, on the conclusion of these notes? Okay, well, have a great day, folks. If you do have questions, I'll be happy to help. Otherwise, I'll see you all on Thursday. We'll be in section, let's see here, 3.5.